Next up, we have Mosimtec, which is actually one of our sponsors for this conference. And they are going to talk about the National Institute of Health and how they help them with their campus parking analysis. So please welcome Jeffrey Skipton and Yusiki Lagarde.
Thank you.
Thank you.
Hello. Hi, I'm Jeff Skipton. I'm with Mosimtec. I'll be presenting today with Yosuke Lagarde. He's another associate with Mosimtec. And we just recently wrapped up a project with the National Institutes of Health, or NIH for short, really focusing on their parking. They're looking at converting 2 surface parking structures or flat parking into 2 parking structures or multi-level parking. And we utilize the road network or road traffic library inside of AnyLogic to do so. And if you want to go ahead and go to the next slide, Yuski. So like I said, we are Mosimtec, stands for Modeling Simulation Technologies. I've been with them for almost 6 years, but I've been modeling, doing simulation modeling for about 20. We've been around for a little over 10 years, so we just celebrated our 10-year anniversary last year. We're very happy about that. We've done hundreds of projects, worked with dozens and dozens of different companies, and basically we provide simulation models and do analysis for a variety of industries and companies worldwide. So next slide, please. So there I am to the left. I'm Jeff Skipton. Like I said, I've been doing models since 2002, so about 20 years. And I've been using AnyLogic for about 17 of those years. So I started using AnyLogic in 2005, many versions ago, and I've watched the progression over the years. I really love the product, and I personally model exclusively in AnyLogic. Before that, my prior life, a long time ago, I have 5 years of experience in developing software at First Logic, which is actually now part of SAP. So have a background in computer science. Yusuke Lagarde has been with us for 4 years, and he's a Duke grad, and he has a background in economics. So he brings a little bit of a different flavor to simulation modeling. I have a computer science background. He has an economics background, and then other associates that we have industrial engineering background. So we're a great organization that just has lots of experience in different things. So next slide, please. So National Institutes of Health, or NIH, and I just want to say that we're probably just going to call it NIH from this slide forward, but it is the National Institutes of Health. They do focus on longevity and quality of life for the American population, basically. And they have lots of initiatives going on at any given time for, COVID-19, for the monkeypox virus. I believe they do a lot with with memory care and reducing memory issues with the elderly, dementia, that kind of thing. And then I'm sure there's hundreds of initiatives that they have going on. They're a large organization, and we, Mosimtec, have done multiple projects with them. And the latest project is the one that we're showing to you now. We just finished up analysis just a few months ago, and we're very proud of it. So next slide. So there it is. It's the down view of NIH in Bethesda, Maryland. As you can see, it's just gigantic. The campus is about a little over 300 acres. You can see some of the statistics there: 98 buildings, 30 parking structures. And this particular project that we're about to show you, and Yusuke's going to really do the deep dive here, starting on the next slide. 2 of the parking structures they're looking to change into multi-level parking garages, and that gave an interesting challenge. Modeling that in AnyLogic. There's several options that we could have done, but we chose one, and AnyLogic, or Yusuke is going to go through that here in a minute. But I did want to point out on the third bullet there, NIH really focuses on health, but they have such a large campus. They kind of accidentally also have to specialize in moving 12,000 vehicles in and out of their campus on any given day. Employees, visitors, getting them in efficiently, not having any backups, getting them to their parking spot, and then on to work or whatever, or their guests, wherever they are coming in. And then one last note before I turn it over to Yusuke is that I've done, I'm constantly making models because I'm a consultant in doing so, and COVID-19 has been brought up on almost every project for the last 2 years, maybe even 2.5 years now. I kind of specialize in quick service restaurants. For half my modeling career has been just doing quick service restaurants, drive-throughs, in-store, parking, and then the approach of the traffic light and whatnot of cars coming in. And I'll talk a little bit about that at the end of this presentation. But as you can imagine, COVID-19 for the quick service restaurants was just an enormous effect because you all of a sudden closed their in-store and everything's now going through the drive-through. So AnyLogic's been a great product, and the road library has been wonderful for modeling that. But so as far as NIH is concerned, I'm going to turn it over to Yuski, and he's going to do a deep dive into the project.
Thanks, Jeff. So the modeling area of this project was the south side of campus, with a focus on the parking and traffic flows in this area. The majority of the vehicles are those of employees, with a small number of visitors included. As you can see on the zoomed area of the diagram, there are 4 primary parking structures. Lot 18 is exclusively visitor parking and is in fact currently being constructed. MLP 7, as you on the right side there, is a 4-story parking structure. However, there is no vehicle movement within it, so therefore it's in essence a 4 surface lots stacked on top of one another in the most simplest form. And so each floor has its unique entrance and exit points. And the primary focus and motivation behind this project was NIH has upcoming plans to replace the surface lot of Lot 42, which currently holds 241 spaces, with a 6-story parking structure. And they're going to name that MLP 12. MLP 12 will have 1,420 spaces, which is nearly a 500% increase in the total capacity from the current lot of Lot 42. So the main requirements from NIH for this project was to understand the impact of different entrance combinations for MLP 12. This primarily focused on the traffic flow patterns, both within the structure and on the surrounding roads. Some of the key metrics for this were the length of time for a vehicle to park after entering the system and to leave the system after parking. Some other metrics include the number of stops and total time stopped for each vehicle in the system. This excludes, of course, the actual parking phase that the vehicle goes through. And they also wish to understand whether increase in parking spaces in MLP 12 was sufficient. So to answer all of these questions, Mosimtec developed a model of the south area of the NIH campus. In general, Mosimtec simulation projects go through 4 key phases. The first is the functional specification phase. So here, both Mosimtec and NIH, we aligned on the project scope, objectives, and we also write out a detailed description of the real-life system. We also agree, I scrolled a little too far there. My apologies. We also agree on the model and project assumptions, the inputs and outputs of the model, as well as the scenarios that will be conducted for analysis and valuable insight from the developed model. Following agreement of the functional specification, the next phase is the model development. We built this model using AnyLogic, of course, and utilized agent paradigms. This simulation environment allowed us to build a model-based application that can be integrated with other applications and other IT systems. It scales well from high-level modeling to detailed process models, where we have a lot of objects and business logic written in Java. So after the model development, Mosimtec conducted analysis of those predefined scenarios from the specification phase, and after which we wrapped up the project with training and knowledge transfer sessions with NIH. Here, we taught NIH how to utilize the simulation model and run their own scenarios down the road. And this way, this whole procedure allows NIH to gain the full value from the simulation model. The key architectural features of this model is that Mosimtec created an Excel front end to run scenarios. We can load all our inputs and scenarios from the Excel into the model. And we primarily used the road library for this model and implemented multiple road networks for the multi-story parking structures. We also leverage stop lines and traffic lights for congestion management logic, both in and around the parking structures. Included in the model are probabilistic travel routes, parking destinations, parking times, and other scenario levers, which are all inputs again from our Excel front end. And finally, after model replications are complete, those outputs are exported back into Excel, which already holds our custom analysis reports. We came across a few key challenges during the development phase of this project. One challenge was converting multi-story parking structures from the Z-plane into a two-dimensional space. Some of the reasons why we elected to do this in a two-dimensional space as opposed to have one road network in 3D is because the former allows simultaneous viewing of all the floors from an animation perspective. Furthermore, given that MLP12 is still in the design phase, it's probable that there will be adjustments to the proposed structure, such as the exact entrance location on any given floor. So by implementing a road network for each floor, architecture changes can be made in a time-efficient manner without affecting another section of the model. Another reason is for model logic and output purposes. So by having a separate road network for each floor, it's easier to have real-time statistics and insight for each floor, including the number of available parking spaces. Another challenge was the control flows of vehicles throughout the structure, particularly at the intersections. An example is implementing a traffic light to represent stop signs so that we have traffic alternating flows instead of just one direction constantly moving through an intersection whilst another is in standstill. We also implemented logic to ensure we were referencing the correct parking lot objects for each parking structure. So for example, on the picture on the right that you see is lot 18. And as you can see, it has 5 parking lot objects. So even though there are other parking lot objects in the same road network, they're located in different parking structures, such as lot 41. So we had to ensure that vehicle routing to lot 18 only parked at one of the available parking lot objects within that structure. And Jeff mentioned earlier about the COVID-19 pandemic, and that did cause some data challenges. And so given the protocols implemented in response to the pandemic, there are currently fewer vehicles on campus compared to prior years. So we had to find a suitable time period to extract the data in order to run scenarios for a pre-pandemic state with the thought of what return to campus would look like following the easing of these restrictions. So our vehicle movement is categorized into 4 main areas: the creation of vehicles, vehicle routing to a parking structure, finding an available space to park at, and then, of course, exiting the system. When it comes to the multi-story parking structures and transforming them from the Z-plane to a unique road network in the two-dimensional space, a key part of this architecture was the use of multiple hash maps. These are populated on model initialization from our Excel inputs. This way, we streamline the code and improve the run speed of the model, since it has all been populated at the start of the run. The use of hash maps also simplifies and improves the readability of the process logic code. Furthermore, by populating the hash maps from our Excel inputs, if there are architectural changes to the parking structures, all that would be required is a change in the Excel front end without any alterations to our underlying code in the AnyLogic model. Throughout this model, we do use about over 10 different hash maps. These that you see on the screen in this table are 4 hash maps that were essential for the vehicle routing in the multi-story parking structures. So the first hash map has a key of stop lines, and the values are an array of parking lot objects. This is used for vehicles parking at surface lots and MLP7, which I mentioned earlier is in its simplest form 4 surface lots on top of one another. When they arrive at the stop line for the structure, which is the key, the vehicle samples for an available parking lot object from the corresponding array. The second hash map is a key of a road network and a value of an array of parking lot objects. This is used in MLP12, which allows for vehicle movement within the structure. This hash map, like the previous one, is used by the vehicle to sample for an available parking object to park at. The difference in this case is that it is sampled when entering each road network, which in other words is a floor. The next hash map has a key and a stop line, and a key of a stop line and a value of a road. When a vehicle arrives at a stop line and is about to exit its current road network. So the hash map is used to understand which road to enter for the next road network. And the final hash map has a road network as its key and an array of stop lines as its value. The stop lines are used to route within the same road network, and this hash map allows vehicles to route to the correct stop line in order to move up and down floors within MLP12. So to ensure that the model was usable and NIH had ownership of the tool, Mosimtec worked with them to design the Excel front end, which includes all the inputs, output KPIs, and dashboards, some of which you do see as screenshots on these slides. So here is a short demonstration. Let me just, here we go. So the blue tabs on our Excel front end are our model inputs. These are the primary levers for our scenario analysis. In the model, we can watch as vehicles route to the entrances of parking structures and park for a duration after finding space and before leaving the system. On the right side here, you see MLP7, and in the center, we can see the 6th and the top floor of MLP12. Each road network uses the density map represented by the colors on the roads to represent the vehicle density throughout the south of campus. And this obviously helps users visually understand the state of their model. We can also see MLP7 here or there, and that allows for movement within the structure. Doesn't allow, sorry. And here is MLP12, and we can only see here vehicles routing up and down and across the floors. And like I said, the 6th floor is on the main network. We can also see the logic here. We have a road descriptor for each network, creation, routing, MLP12 movement and parking, and finally MLP7 parking and the other lots, as well as the models exiting, the vehicles exiting the system. After the run is complete, the outputs are exported back to our custom Excel workbook. And these outputs are the green tabs that you see. And each tab has customized reports and graphs. There are also filters available in these reports too. So the value we created from the simulation model allowed NIH to understand that in the current pre-pandemic state, all the proposed entrance combinations for MLP12 do not significantly affect the traffic on the surrounding roads. Furthermore, we were able to compare the metrics of the vehicle journeys through the system, such as the length of time stopped in transit amongst different parking structure entrances. These metrics were considered pivotal so that NIH can continue to prioritize on-campus experience for their employees. And as mentioned earlier, some of the metrics were the number of times vehicles stop and duration stopped whilst in transit, time to park after entering the system and time to leave the system after parking, and the parking structure utilizations. All these outputs can be filtered by the overall system and by parking structure and even by each individual entrance and exit location of all structures. The next steps from here are for NIH to continue exploring the impact of different entrance combinations at MLP12. There's in fact already discussions to change the current planned locations to different areas around the structure. Given the architecture of the model, these changes can be seamlessly adopted and implemented. And as COVID-19 restrictions ease, it is important to update the input data. And so this includes the number of daily vehicles, parking structure weights, and the duration vehicles are parked. There's also the possibility to expand this model from the south of campus to the entire campus and even the surrounding roads. I'm going to hand it back to Jeff now to talk on how these techniques and can help other areas outside of NIH.
Thank you, Yusuke. We have a couple more slides, but I encourage you to ask questions, just send them in, and we'll do our best to answer them. We'll have a few minutes at the end of this presentation to answer those. So beyond NIH, and we're really just talking about other uses that we've done with the road traffic library outside of this project. As I mentioned before, I've done quite a bit in the quick service restaurant industry, and we have used the road traffic library extensively for modeling the drive-through, the parking lot for in-store customers. And then in the last few years, we really expanded out to the traffic light and really going out 2 or 3 or 4, maybe a quarter mile of the restaurant and modeling the approach of the cars. So the egress and the ingress. So we also have to get them off the property, which is sometimes can be more difficult than getting them in. And we have been involved with brand new restaurants and have come up sometimes with conclusions that perhaps it's not the best place to put the store because the surrounding network isn't capable of really supplying the vehicles or the route into the store and then exiting the store, with the number of transactions that they're going to be doing per hour. I do want to note that we've used out of the box, the road traffic library is wonderful, but we use the stop lines, and then I particularly just manipulate the car. So when a car goes across the stop line, I can see where they're at, and I can see if they're at a window, for example, to get food or to make a payment, or if it's outside service, they're next to somebody that's trying to take an order. And then we just trick the car by setting its preferred speed to 0. It stops the car and then throws us a nice event that says, hey, I'm stopped, I need service. Once the service is complete, we can just set the car's preferred speed back to 5 miles per hour or whatever it happens to be, and the car can move on. We've also integrated the pedestrian library in with the road traffic library, and I've done some tricks to get them to be able to see each other. Some of the tricks are available online, so thank you for those people that post those tricks, and we've come up with some of our own. But that, we've used it quite a bit. So if you haven't used the road traffic library, highly recommend it. So next slide. So Mosimtec would like to thank NIH. They gave us a great and quick approval to go ahead and share this project, and they've been great clients to work with. And then lastly, Mosimtec can be reached at our virtual exhibit booth. So please come visit us. We're there, we're available, and we'll answer your questions. You can also visit us at mosimtec.com. And I'd like to point out, if you are a student, we do have internships over the summer. So reach out to us if you're interested in one. And then also, if you'd like to be a consultant, a simulation modeling consultant, and join our team, we actually have a job listing right now for one. So please contact us, through our website or at our virtual exhibit booth. So we have 3 or 4 minutes for questions. I see a few coming across. Yusuke, did you get a chance to look at them?
I did. I can take a couple of these here. So we have a question here that says, how did you represent the human behavior of which level to park on inside MLP12? That's a great question. It isn't a case that we just fill up one level and then we start moving. We actually have an input of the model, so that is a threshold, a percentage threshold, that dictates at what point of the floor being filled do you consider moving up or down. So for example, if that input is 60%, that would mean that once that floor has reached 60% capacity, then the vehicles consider moving up, down, or stay on the same floor. So using those hash maps, we can evaluate how many available spaces are there above me, how many are available below me, and how many are available on this floor. That's what you often see when you enter parking structures with your lights and your updated statistics. And then from there, based on the proportion of available spaces, we sample for just the probability of which floor, if you're going to go up, down, or stay on the floor. I hope that answers that question. So then we also have a question of, can this model be used to evaluate any exclusive parking types such as valet, handicap, or electric vehicles? In the current state, I would say it is not possible, but it would just, all that would require is adding some extra columns to our Excel inputs and then dictating that these parking spots are exclusive to certain vehicle types. So we already do that with the visitors in lot 18. So it would just be adding more categories such as the valet, handicap, and electric vehicles there. I also see another question that asks, did you incorporate any pedestrian flow in this model? In the current state, we have not got any pedestrian flows in there, but we are in discussions about adding that. So adding some pedestrian flows, which, it is a case of, if there's data available, it makes it very, very realistic, such as, did vehicles carpool? Which direction from the parking structure did they go? Did they go north, south, east, west? So there you can look at things like attendance in buildings and directionally to figure that out as well.
I think we're in the last couple of minutes here, but there's another question that came by, which is a great one. Why we used Excel for the inputs and outputs. And the answer to that is we use Excel quite a bit for our projects because it is a file that holds all of the scenarios inputs and outputs, obviously, and reports all in one spot. So basically it becomes a scenario. The user can simply copy that scenario, rename it, and it becomes a new scenario. So then they can enter that second or third or fourth or 100th or whatever Excel file, change their inputs, run it, and then the outputs come out of AnyLogic and automatically into Excel. We have done in the past, not for this project, but we have had our inputs in AnyLogic, and that works well as well. Sometimes we save those off into XML files or some kind of flat file so that we keep track of our inputs and outputs directly from AnyLogic. But in this case, we just decided to use Excel. There's another question that came wrong. I don't know if we have a time for this.
Says here, can the model be used in other similar problems? I think the model can be used in a lot of different ways, such as, not if we're talking about just exclusively for NIH, we can look at what does vehicle movement in mass emergencies look like, such as an emergency that requires everyone to leave campus immediately in vehicles. What does that look like? So that's in a small scope of NIH. But then in terms of other industries, I think you can apply what we showcased today in, like Jeff mentioned earlier, drive-throughs, procedures, parking structures, just simple construction and operations, and see how that impacts vehicle movements in the surrounding roads.
Okay, I think we're out of time. Another thank you to AnyLogic for allowing us to present, and come visit us in our virtual booth. It's Mosimtec. Thank you.
Thank you so much, guys.
Awesome. Thank you guys for that awesome presentation.